Hello all. Here we are to the next numerical on equivalent static method. This is a numerical picked up from the textbook. Code was not revised then. So I request you to look at the procedure and solve according to the new code. That would be treated as your assignment. I will be giving you the dates when to submit them. So we'll just go through a couple of examples more. Reading into the example. For a residential RCC special moment resting frame. So he's already telling us it is a special moment resting frame. Building shown in the figure below. The seismic weights on the floor are W1 is 294.3 kilonewton, W2 is 1863.9 and W3 is 1079. So W1, W2 and W3. W1 being the roof, W2 and W3 are floors. Roof weight is less than the floors. And the story stiffness are given to us. I'll get back to the story stiffness later. The story heights are, the ground story is 4 meters, that is this one is 4 meters. First story is 3.2 meters and the second story is also 3.2 meters. Founded on hard soil and situated in zone 4. So we know that it is in zone 4. We'll have to pick the Z value for zone 4. The free vibration results. So now the stiffness values and the free vibration results which are mentioned over here, this is for dynamic analysis procedure. This particular example is from Vinod Asur textbook. So we will not be doing the dynamic analysis now. So we'll just stick on to equivalent static. When we are doing dynamic analysis, I'll get back to the same numerical again. So now required for us data is for equivalent lateral state, natural period, and zone. So zone 4. So where do you pick zone 4 value? Zone 4 or zone Z value is picked up from page 10 of your code book, this one, right? So zone 4 is 0.24. Okay, so zone 4 is 0.24. Here also it's the factor is 1. This is according to the old code. Now importance factor, I have to go to page number 19, right? So page 19, I have the various importance factors mentioned over here. Now, what type of structure has he told us in the question? It is a residential RCC building. So when I look into this, 1.5 of importance factor is for all the important buildings, and residential or commercial buildings other than these are 1.2 and all other buildings is 1. So here you can go ahead with, because it is a residential building, as 1.2 or even with 1. To be on a safer side, it is better we take the I importance value to be 1.2. So what you will consider here now in the numerical is I is 1.2. Response reduction factor, in the question it is already told it is a special moment resisting frame, and we know that for special moment resisting frame value is going to be 5 from table number 9, page 20. So you can go through the code book. Okay, then after writing these data, I have to calculate the natural period Tn to find the acceleration, design acceleration, right? To find the natural period Tn, we have a set of formulas for Tn on page 21 of the code book. So let us just go across page 21 here. So these are your few of the values. So it is a RC moment resisting frame. So Tn is 0.075 h raised to 0.75. That is what is used here, 0.075 h raised to 0.75, because it is a RCC special moment resisting frame. So R is 5, and substitute in this h. H is, we know the space is how much? 4 plus 3.2 plus 3.2 total height. Substitute for the total height and get the value Tn. Okay, for this particular Tn for hard soil, we have to pick the SA by G value from the table or from page 9 of your code book. So coming back to page 9, to get the SA by G values, we have a set of two tables over here. One is for static method, one is for response spectrum method. It is a hard soil, so here we fall under this category, and the value that we are getting Tn is 0.434. So 0.434 lies from 1 by T, that is 0.4 to 4 seconds. So I'll use this 1 by T for finding the SA by G value, and I get the SA by G value. Please substitute according to what we are getting data. Okay. Then once that is done, the horizontal coefficient or the design horizontal seismic coefficient AH is given by Zi by 2R into SA by G. Z is zone factor divided by 2 constant. I take 1.2 and R is response reduction factor equal to 5. SA by G value you have calculated from the natural time period, you get a AH value. Then total seismic weight we have to calculate to find the base shear. Base shear is given by AH into total weight. So total weight in this particular question directly given to us as W1, W2, W3, which are in terms of kilonewton. If it was kilonewton per meter square, I'll multiply it by the area. Now I will directly add total weight is W1 plus W2 plus W3, which is this. So base shear is given by AH into total weight W 0.055 into this value. I will get a base shear of 178. Put up a table for computation of lateral forces as at each, starting from roof, second floor, and first floor or first story. So I know the weights, make a note of weights from the base, the heights. So total height is 10.4, then it is 7.2, and this is 4. Wi into hi square column, Wi hi square divided by summation of that, I get a column, multiply by the base shear, I get these values. So once you get those values, we will be showing the diagram of distribution of story forces and story shear. It's a very simple problem as compared to the previous one where the weights are directly given. Consider this to be one of your practice examples. Coming to the next example from the same book for an RCC OMRF, that is ordinary moment resisting frame. Now we know SMRF, it is going to be 5. This is an ordinary moment resisting frame. The response reduction factor is going to be 3. Please go through the code book. Building frame for an office. So importance factor is given in the question. This is a office building. What we can do is we can take 1.2 or 1.5. Okay, because we have not mentioned what type of a building. It is not special moment resting frame, so we can go ahead with the I value to be 1.2. The loads on the floors are dead load is 8 kilonewton per meter square on each floor and 7.5 kilonewton per meter square on the roof. The live load is 4 kilonewton per meter square on each floor and 5 kilonewton 1.5 kilonewton per meter square on the roof. These are the live loads given on floors and roof, and dead loads for floors and roof. The story heights are ground story. Here is the figure is 4.2 and rest 3. The building frame is 4 bays of 5 meters each. So 1, 2, 3, 4. This makes it 4 bays of 5 meters center to center distance and founded on the hard soil situated in zone 4. The plan and dimensions of the building total plan is 20 meters by 20 meters and total height of the building is 13.8. I think we have done something similar example. Here the damping in the structure is 7%. So they have given me the percentage of damping, that is 7%. Okay. So from this, first we will pick up the values, that is CC, OMRF. So response reduction factor is going to be 3. Importance factor take 1.2. And dead load, live load, total height you can calculate. Zone 4. For zone 4, what is the Z value? You will be picking up from table 3, page number 10. And we will be calculating the rest of the values as follows. So floor area, it is a 20 meter by 20 meters, so 400 meter square. On the floors, 50% of the live load has to be taken. No live load needs to be considered for the seismic weight at the top. So 400, that is total area, into dead load is 8 kilonewton per meter square, and 50% of live load, that is 0.504, 4000. And seismic weight on the roof is only the dead load into the area, that is 3000. Now considering the frame structure with brick masonry, calculate the TN value. I think we have done the same example. Multiplication factor for damping. Now the change over here is the damping. Now what is this damping? In the previous code, old code, there was a damping factor which had to be multiplied. In the new code, they are not considering anything for the damping, so you can currently ignore this factor for the damping, and with the other given data, you calculate the AH value, that is design seismic coefficient with ZI by 2R into SI by G, substitute, and total data we have calculated. Get the base shear, put up the table, this is same like the previous example, put up the table and find the distribution at each of the levels. Okay.